It takes a few seconds. Let's see, I have another terminal here. Funny. Oh, okay. It's already working.
Okay, good.
This always happens. So, good afternoon. It's my pleasure to welcome you this afternoon to the colloquium of our department. And today we have as guest Professor William Rundell. I know Bill for a long time. I think since the first AIP in Montecatini. Do you remember that meeting in 2001? So long ago. Bill is a professor at the Texas&M University, and he works mainly with inverse problems and inverse scattering. I just checked his CV. He already published over 90 scientific papers and a very well-known book, together with Lassi Pavarinta and Colton, about inverse scattering and inverse spectral problems. And it's my pleasure to present to you this afternoon Professor Rundell, and he's going to talk. Sorry, I just can't see your slides.
Okay, let me close off and go to my share screen. Can you see my slides now, Antonio?
Not yet.
Oops.
No, we just tested that a few minutes ago. So,
yeah.
But I just found, so he's going to talk about recovering coefficients and terms in the reaction diffusion equations. And the slides are here. Okay, everything is set.
Okay, thank you very much. I'm glad to present this talk. I'd like to thank Antonio, of course, for the invitation, but actually I've got something else to say about Antonio. We have known each other for a long time, and at least I'm very grateful that 3 years ago, roughly, he invited a large number of inverse problemers to IMPA, and I gave a talk there. And then, although I've known Barbara Kaltenbacher for a long, long time, during my talk, she asked a question which turned out to have I have no clue how to answer it. So we talked about it afterwards, and we're now working on paper number 10 together. So this is an amalgam of results from a few of those papers. And so again, Antonio, for the introduction to Barbara, so to speak, with the opportunity to do this, and that is, of course, very, very pleased that this has worked out. Anyway, so I will also say at this point that there are two parts to this talk. There's the not so good parts, that's what I did, and there's the parts that are really good, and that's of course what Barbara did. And let's move on. So I'm going to start with things you might not expect. So this is population dynamics, early days. And you're measuring, of course, a population at discrete set of points. You've got some idea of an initial condition. And the first publication here was 1798, where Malthus's model, P prime is R, P is famous. To be truthful, he was not a mathematician. He was actually an Anglican priest, and he had motives for doing this, that he wanted to have a social agenda that had birth control and the rest of it as part of it. So he of course worked out what year it would be from data collected from what he estimated R would be from the difference of deaths and births in his parish. He calculated the value for R and worked out which day in the future there would only be 1 square meter per person unless something was done about it. Anyway, more scientifically, and probably one of the great, shall we say, inverse problems from the middle of the 19th century was by the Belgian, I guess you would call him a mathematician in some ways, because he was pretty mathematical, but he was interested, of course, in population dynamics. And he got US census data for 1790 to 1840. Every 10 years, there has to be a census in the US. There's one this year. And so here is the data that he got, because it's public record. And that's the number there in millions. So you look at the differential equation for P prime, and you take logs, and you get log of P minus log of P minus K is RT plus C. So when you've got that, of course, this tells you that if you knew K, you could find R, but it doesn't matter. If you could find the right value for K, this would be a linear equation. And he used this to pretty good effect. He tinkered with K to get a straight line. When he got that straight line by the eyeball norm, the slope was R. And then he used least squares to obtain the best error fit for E. He minimized E, and there he went. So he got an accurate figure for another 100 years. The error he would make in computing the steady state was accurate to within 1% until around about 1940 or so. Of course, things changed in the world. It's quite a robust calculation of R. But when you look at the sensitivity for K in the eyeball norm, basically, any K bigger than 80 million gives you a very good looking straight line. And so when you look at the sensitivity here, you see, look at the scale. The minimum, as he says, 178. But when you look how flat that curve is, this is not an easy numerical problem. So moving on, 100 years ago, epidemic models and the famous SIR, or the Kermack and McKendrick models, is a coupled system of 3 equations and 3 unknowns. Those who are infected, those who are susceptible, and those who have recovered. And you assume a fixed population. This is over a short time. And you have 2 magic constants here, one also called small k. And the other one is called the beta. And it's really the ratio of these 2 things that's important. One is the relative removal rate, and the other one is a contact number, often called R0. The game is to get R0 less than 1, because in that case, if it's less than 1, I is decreasing, and the epidemic is going to die out. The catch, of course, is that the sensitivity in these coefficients, and you saw how bad it was for the Verhulst equation, it's worse here. Except the data, of course, for these models is not very accurate. The estimates on the true number of cases over the reported number varies from country to country, but it's usually thought to be around between 200% and 1,000%, factors of 2 or 10. And in some countries, of course, like the one I'm living in currently, this is not surprising, since the president has declared that the best way not to have an epidemic is not to have any cases. And if you don't test, there can't be a case. So anyway, the problem is that this whole series of models depend on calculating constants in a fixed and rigid model, either the Malthus, the Verhulst, or in this case, the SIR. So people then started to look, of course, in the 20th century to add in things like spatial dependence. And Fisher and various other colleagues in the 1930s published a lot of seminal papers of ecological models that took into now not just ODE models, but a reaction diffusion equation, K here being the diffusion coefficient, And again, typically they took Verhulst or logistical terms for the forcing function f of u. 1930s, Zeldovich and Frank Kamenetsky again looked at combustion models of the same type, and they used a cubic in there because the differences between a cubic and a parabolic is that the parabolic simply goes up to a top and comes back down again. The cubic can have another turning point, and that is critical for their modeling. The problem again is the same thing. It's A, B, and C, or B and some other constant you've got to get. So now we're moving on. Turing looked at systems of reaction diffusion equations and proved some absolutely, but this is the same Alan Turing of Turing machine fame. He looked at, in R2 and R3, coupled systems of equations and showed that they can have periodic solutions. The standard trick here in chemistry experiments for younger children is to have a glass jar filled with a chemical which you mix and it turns red. And then he lets it sit, and then in a couple of minutes it turns blue on its own, then back to red again. And this is simply a coupling of two chemicals that fade in and fade out through this coupling mechanism. But again, now, what is the coupling mechanism? Traditionally, in ecology models, it's always the interaction is UV, the product of the two quote species. And this is always the case again in early chemical reaction papers. But later on, for example, the Gray Scott from about 1960s, 70s took an unbalanced one of U squared V. And the so-called Brusselated equation of the 1980s took a coupling term which is much more sophisticated, Bu minus Cu squared V. But here's the bottom line here. In every case, there's a modeling choice. You invent what you think is happening, in this case, on the F of U term. Or in the previous case, it was the population, whether it was R times P or quadratic in P or whatever. So now, what's next? Well, in this case, the choice of all these functions and the hard wiring in of a known F, except for constants, a known phi, and a known W, except for constants, this is the domain of the mathematical modeler. And recovering these constants is now termed distributed parameter systems, and inverse problems for these have been studied for many, many decades. So now, what next? Well, what Barbara and I have been trying to do is to make no assumptions on the specific form of F of U. Well, we need regularity, and we need some natural physical constraints, for example, positivity. We're going to measure data within the domain, either on the boundary as a time trace for time values, or in some curve, maybe a later time. And I want to know, can we use this data to recover the function f as a functional form? Of course, in practice, you've got discrete measurements. So how can you get a functional form from discrete measurements? Well, one possibility is you up-res your measurement, a finite number of points, into, let's say, a cubic spline, and then use the functional form of that as your new data. Or you can write f in a basis set, say Fourier, moving Gaussians, radial basis functions, and recover the coefficients under the assumption that those coefficients basis size can be as large as possible. So if you get n measurements and n less than n basis points, then the inverse problem again becomes parameter recovery, but with differences. Now you've got questions like, for a given noise level delta in the measurements, how large can you choose n, the number of basis elements? How do you regularize this problem? And is there some convergence as your data measurements tend to infinity for the number of basis elements you can get? And what if you get multiple unknown functions? How does this go? So there are going to be two specific data types we're going to call them final time. We measure the value on some kind of curve in space at some fixed time. You might want to think about this as a census. You could, for example, measure a species by flying helicopters, planes, drones over the savannah and taking photographs and then doing a count of that time you took the measurement. Or you can be at some fixed point, presumably on the boundary in a physics experiment, and you would measure either the value of U or the flux, depending on which one was your original boundary conditions. So those are the two types we're going to be talking about. So I should tell you right now that I'm not going to cover f of u over any kind of range that appears in the differential equation unless your data also has that range. In other words, you've got to set the problem up so that your range of u over the entire domain is a subset or equal, obviously equal to the range of u over the measurement set. Okay, and that is absolutely critical. So in the usual undetermined coefficient problems, the equation is linear or any nonlinearity is detached from the unknown. The domain of the coefficient is known, omega, some time interval. Regularity theorems from the coefficient to solution are relatively straightforward. But in this case, when we're trying to recover the nonlinearity, all of these are going to fail in some way or other. So, for example, the range condition may only be a subset. There's also regularity problems. If f, for example, is just continuous, that doesn't do you very much actually in a parabolic equation. You should go into Sobolev space, so it's actually a little bit easier to see if you go into Schauder space. So if f is in C0 beta, it doesn't follow that ut of f is in C1 beta. The regularity pickup tells you you get C2 beta in space and C1 beta upon 2 only in time. This causes enormous problems for the analysis. And you might think going into Sobolev space fixes it, but no. The Sobolev embedding theorem between these two tells you that you don't make these things vanish quite that easy. You've also got to worry about the growth, for example, of the nonlinearity. If it grows superlinearly, there could be blow up in finite time. That's not a problem if you measure things before that time, but in general, this is not a reasonable way to go. The condition is very delicate and it depends on spatial dimension. But there's good news. The problem turns out to be often less severely ill-conditioned as measured by norms. And the term f of u is a dominant term. And there's a folk theorem, there's many folk theorems in inverse problems, but one of them is that if you're trying to extract a unknown in a differential equation, and it's a dominant term in the equation, it's easier to get because it dominates the data. On the other hand, if it's the other way around, then the inverse problem is much more ill-conditioned. Okay, so this is part of the good news offsetting the above bad news. But what it means is we have to distinguish between you giving me a pre-existing data set and telling me to recover f, because it's unlikely if you just take some random pre-existing data set, it will probably not satisfy the range condition. And so instead, you've got to think about choosing your input values in the experiment in order to accommodate that condition. You're also going to have to worry about regularity results, and you'll see that as we go along. So this is the difference here between a found experiment and one that you can actually adjust the modeling on in order to make this part work. It's critical. So it turns out there's two natural approaches. How do you find unknowns? Inverse problems, Newton-type methods, of course. But there's also another thing that we've found to be just about always as good and sometimes much better, is to map the PDE onto the surface that you have your overposed data on, and then try and solve for f of g, where g is your data, iteratively. And that's going to be, in fact, more the theme of this talk than anything else. So here we go. Now, if you look at the previous differential equation, I'm suggesting you look at the map capital T of f, which is ut at a final time, minus your value of L of g, g being your spatial measurement. You have to hit it with L. Of course, that's a problem because when you have your final data g and you're hitting it with a differential operator, you are losing regularity, and you're going to have to make this up somehow in the model. On the other hand, you can see that the loss of regularity here is, well, if it's a second order operator L, you're going to have two derivatives taken on g, which you have to invert. But a two derivative loss in an inverse problem is no big deal in comparison with many cases. And look at the sequence of approximations given by the obvious iteration scheme. And as I'm going to show you, this works enormously well under a broad range of conditions. Okay, but once again, I want to keep reminding you that before you can make this work and before you can even write the above map, you must ensure that the range of u over your domain is contained in the range of your measurement set. Okay. As you do these iterations, namely the FKs up here, you can pull the solution out of that range. You're going to fix that. So you actually have to go and pull it back in again with an operator P, a projection. And that's a critical part that's needed. In the end, as you converge, of course, your range condition will work. But there's delicacy involved. Now you'll see that if you look carefully at this slide, as the text gets in the last two lines, it starts to fade out. That's because I want you to see it, but not to actually read it, because the conditions are actually quite technical. But to hide not the truth from you, but hide the bitter reality here, these kind of estimates are part of the game. So anyway, from all of this, you get a theorem. I've got a certain set W, which was one of the ones in gray above. And if F1 and F2 are in that set, then there's a constant C, depending only on the second derivative of F. So I need obviously assumptions on F. And guess what you get? You get a Lipschitz condition on T of F minus T of F1 minus T of F2. And the constant is some C e to the minus a term, and it contains the eigenvalues of the operators L, and the bound therefore could be made in terms of the largest one, which is the lowest eigenvalue. Wonderful, because what that tells you is there's going to be a sufficiently large time t such that, or t star, that if you take t bigger than t star, there's at most one fixed point of t in omega, and thus the solution of the inverse problem, if it exists, is unique. So that is why this idea of mapping is quite powerful. You have to set the conditions up, and those things I've grayed out for your inconvenience or your savings of mental thought about what it all means is the key to the whole game. Once you have that, you've got that self-mapping, and you've got the contraction, of course, then you've got a proof that the iteration scheme will converge. Okay, so it's picture time. Reconstructions using this operator. So here we go. This is a cubic equation as a model. In fact, it's an equation that's very like the numbers that would come in from that combustion experiment that I mentioned earlier on. So there's a 1% noise in the data and a 5% noise. I've got, as you can see, a couple of iterations. The first one is red dots. And after that, there's a green dot, but the green dots get pretty much taken up in the reconstruction. And this is a really good reconstruction. And the one on the right is probably under-smoothed a bit, but it shows you how well the thing follows from 5% noise. The convergence rate here, the value here was T was 2, final time, but the convergence rate is much more rapid with greater T, as you can expect from the last slide, which, if you look at the Lipschitz constant in the fourth line from the bottom, T appears in the exponential term. Larger the T, the smaller that Lipschitz constant will be. And that's exactly what you get. Now here's a much more complicated, in fact, piecewise C1 function now. This is only in C0 beta, well, actually C01 with beta 1. But it shows you that even 1% noise here, and again, final time, this is a pretty good reconstruction. And I think that reconstruction is about after 5 iterations. And in both cases, they started from F is 0. So this works really well. Now, Newton, on the other hand, with 1%, I've shown you 2 functions, 2 different trial ones. The combustion one on the left and a highly oscillatory one with the peak in it, that second thing on the right. And Newton's does not do so well here. This is 1% noise, the same as the one previously. So you see that in comparison, and these, the one on the right took quite a bit of regularization, constant tampering with to try and get a good answer with the discrepancy principle. It's non-trivial to actually get this to successfully work. So Newton works, but not nearly as effectively. So here's now time trace data. And let me point out to you an earlier thing that I said. If F is in C0 beta, then in space, the solution is in C2 beta. And that's what you just saw. This was time, final time data. I was differentiating the data with respect to the operator, but that just brought me back into the space again. The 2 derivatives knocked my 2 beta regularity back to beta. Good. Now with time trace, there's a slight difficulty because when you do this, you're now going to lose a half exponent on each iteration. And the question is, can you prove something here? Well, in the other case, you noticed that I showed you a analysis and a convergence result. I'm not going to show you one here for a very simple reason. We don't have one. But the pictures work reasonably well. But again, you see that there's an important term. This is a coupled here now system, and the beta has an effector. This is the coupling between the two. If beta is small, the thing works out quite well, and I recover an F1 and an F2 quite well. The noise here, I think, is less than 1%. I think it's maybe only 0.5%, or maybe even 0.1%. But if beta gets larger, for example, 1 or 1.3, then the iteration process, especially for large times, really slows down. You can see the convergence is happening, but the number of iterates is actually quite large to get the endpoint values. And this is typical because the coupling here between the two gives you an interaction that with uncoupled, it's just the same as each equation. If beta is 0, you're doing the problem twice, one for an F1, one for an F2, and there's nothing to talk about other than that regularity result I mentioned. But there you see the difference of what happens in coupling. So now I want to go to assuming that I know F1 and F2 for whatever reason. And now I want to know about the coupling term. Can I recover the coupling term? So I've got a phi1 and a phi2, and I've got a function w that couples them. So in what I'm going to do next, I'm going to take w to be just equal to u times v, although we'll talk about that later. I take two values of F1 and F2. I've taken logistical models for both. And I've got two values of phi1 and phi2. And as you can see that one is smooth, but with oscillations, and the other one is a polynomial cut off, so it's no longer C1. Okay, so the pictures here are showing the reconstructions of phi1 and phi2 depending on the coupling constant beta. You can see again that the value for beta makes a huge difference, but the recovery of the numerical scheme, again based on projections for final time, is actually quite good. We are converging to the correct values, and the smaller beta is, the better. Okay, but now you're maybe tired of these non-linearities and their issues, but surely my linear inverse problems behave even better. Let's go see if that's correct. So now the game is, in the reaction diffusion equation, there's a reaction term, that's the F I've been talking about. And the coupling terms of the various Fs, they're all reactions. But there's also a diffusion term. So now I've written things down with a linear equation to see what the differences are. And I'm into trying recovering partly a reaction term in the Q of U or the Q of V, but Q here is an unknown coefficient. So I'm assuming here I have modeled the thing with a linear reaction term, but that term could vary over space depending on where I am. I'm also assuming I've got a conductivity, if you will, A, or the diffusion parameter in ecology models A, and that also depends on A of X. I'm going to run this coupled system together, and I'm going to run them from initial data, and I'm going to run them with different forcing terms, R of U and R of V, running two experiments, and I'm going to measure the values of U and V at a later time, capital T. And the question is, can I recover the pair A and Q from this simultaneously? Well, again, we could Newton this, and I'll show you a picture, but we'll like to this same trick of evaluating the differential equation pair on the first set of equations at the top. I want to project them onto the line T is capital T, where I've got my data measurements. And when I do that, then since I've got a linear equation, I have a linear mapping M on the two unknowns A and Q, taking on the value of F of A and Q, where F of A and Q is everything that's on the right-hand side. But of course, that's non-linear. The value of U depends non-linearly on A and Q. So this is a linear left-hand side for A and Q, given by that matrix, and a non-linear term now, F of AQ, that I have to solve. This was only a linear equation. This was not a linear inverse problem. Okay, so that's just a statement of what I just said. And the strategy now, of course, is to try and invert this operator M, look at M inverse on F, and call this my new map capital T. And I want to know, is there conditions I can set on things for which that mapping is a contraction in a suitable space? So The best trick that we know of here turns out to be to multiply the first equation by your data GV, the second one by your first data GU, subtract and eliminate Q. Of course, this depends on the fact that we've taken a linear assumption on our F of U, namely that it's Q of U. So when we do that, we end up with what we've called the Wronskian, it is a Wronskian, and a whole series of terms, phi here, which we can compute for a given A of Q. And then, since we know the value of W on the boundary, we can then solve this system to get a iterator procedure. Of course, it's nonlinear, and it comes as some integral over the region of our measurements of some function phi given by this horrible combination up here, depending on A and Q. And the question is, what happens to it? Well, the first thing you notice is there's a term outside 1 upon W. So the Wronskian, we've called it, can't vanish, and that's in a condition you have to impose on your data. And there's ways to do that, but if you don't do it, you're going to have severe problems, and this matrix M up here, or this operator M, will not be invertible if that's the case. An alternative is to eliminate Q by, again, this similar multiplications. And when we do that, you get an uncoupled system for A. Once you've got A, you throw it in and you try and recover Q. The problem here, this requires you to have both W, and you can see the equation that's fourth from the bottom, and the gradient of W. Well, W is not so badly behaved, but the gradient of W, I'm afraid, could be a real problem. In fact, the gradient of W could certainly both vanish, and not only could it vanish, it could vanish at multiple points, and it might even be a large term. So it turns out that this alternative, while it looks attractive to separate them, is not necessarily as effective as the coupled version that I just mentioned. Anyway, in one space fit things, you can use inverse Sturm-Liouville theory, eigenvalue expansions. And if you do this, then you can get a series of lemmas on the contractivity of the eigenvalues and eigenfunctions depending on A1 and AQ. This is a standard Sturm-Liouville theory for elliptic operators. And then you use the representation for the linear equation up above for a single one, or for a double one would be much similar. I've just kept it for single. And in the end, what you end up with is showing that, again, you've got exponential terms, and when you put T to be capital T, those exponential terms decay at least as large as the lowest eigenvalue of your operator. And you can prove then that T sufficiently large, the Lipschitz constant will be less than 1. Okay. Now, the bottom half of this picture tells you what you might expect in higher space dimensions. You can forget everything I just said to you about inverse Sturm-Liouville theory, because that's all dependent on special cases for R itself, R1. There's no such thing in R higher dimensions, because in R1, the eigenfunctions are linearly independent. They're all single. There's no duplicate eigenvalues, but this is certainly true in higher dimensions. And now you have to go and work a lot harder. So there's a whole series of conditions which I've sort of put in gray again. Not that you should worry about this, but there are technical conditions, and I could promise you that when you look at the paper that this is based on, there are many, many pages of technical conditions which I haven't put down. But again, you can prove that for T sufficiently large, that is a final time T large enough, the operator is a contraction with respect to this norm AQ that has been put down there, which is a sum of L infinity norms on L2 norms for AQ and A prime. And so there's obviously regularity results hidden in here. Okay, and finally, some more pictures. let's see how well the reconstructions do against the reaction diffusion case of getting the F's and the P's in that. First of all, I want to draw your attention to the top left picture. This is the singular values of the map T, coming from the A and coming from the Q. You see that the ratio here of these starts out at the small singular values to be a factor of about 50. And at the end, it's a factor of about 150 to 200 between the singular values for A and the singular values for Q. What is this telling you? This is telling you that the term A here, the conductivity in the equation, dominates everything. And recovering, therefore, A is much easier than recovering Q. In fact, Q here is with under even modest sized noise levels is hidden in the noise. The figure to the right shows you the value of W and shows the value of W prime. Notice in the case when I tried to uncouple, I needed 1 upon W appearing. I'll go back and show you that. There was this term, I had A times gradient, and I had the, sorry, we'll go back again. The second last line there, my update scheme had a 1 upon W. Notice now that what's happened here is W vanishes at points. You've got to take this into account as a separate regularization. Notice also that W prime vanishes as a gradient in one dimension, and that was another problem. But look at the size of W prime, and that's why that elimination scheme turns out to be quite poor in comparison. So if you do it in parallel, the one that's recommended, you see that this is 0.1% noise to show you that a little bit noise is okay. The A just converges rapidly. And that's because of the singular values up there are large. The Q, even with 0.1% noise, is never completely reconstructed. The dashed line is the actual one, and the one that you're seeing that I get here is, sorry, the bold line is the actual one, and the dashed one is the reconstructed one finally. And it's off by a fair amount. Not surprising given the picture in the top left of the singular values. So there's one more thing to show you, and that is the variation of the convergence with the final time value T. Here I've only shown you the case of the A, the one in the left middle up here. And I've shown that to you only for 2 times. T is 0.1 and 0.05. And you'll see there's a big difference between the two in the first iterate. They're all doing actually pretty well. This converges rapidly, as you saw from up there, but the convergence scheme really does. Even the first iterate, you can see the effect of doubling your time T, and you get a much better estimate much quicker. So that is the end of my tale, and I thank you for your attention, and I'll be happy to take any questions. Let me see if I can come back to my face. Does this now show me?
Okay.
Yes. Oh, thank you, Antonio.
Oh, you're welcome. So thank you, Bill, for your very nice talk. I would like also to mention that we have another guest here. She is also present here in the chat. So Barbara, Professor Barbara Kaltenbacher from Austria. She delivered a talk a few weeks ago, maybe a month ago, here at the colloquium. Please, Barbara, don't be shy.
Barbara volunteered that she would answer all the questions.
No, I will not answer all the questions. Actually, I wanted to pose a question, but I should not be the first to go, so maybe there's someone else.
As you can see in our chat, in our YouTube chat, the students are usually very shy. So maybe you can start, and because there is also a delay between our transmission and the YouTube, maybe they will pose their questions later. Please, Barbara, you can start. You're the guest.
Okay, so thank you.
I'm getting very worried here.
No. I mean, as you pointed out at the beginning, for these nonlinear models, for instance, in population dynamics, there are certain properties of the solutions that you would expect to hold. For instance, that they don't grow unboundedly, but there's some saturation or something like this. Do you think it is possible to impose something like this as a constraint in the reconstruction? So properties of solutions and of the functions themselves?
We haven't, right? The question is, would it help? I think the answer is yes, but can I go back to the describing for example, the cubic model? Might be hard to get back to it in real time. Go to page 3, further on. Okay. The fourth line in this page is a cubic. A of u, b plus u, c minus u. Let me tell you the values here. C is small. So what happens is A, B, and C, of course, are all positive constants by definition. The way you write these things down, but C is small. I'm sorry, C is large. And so in the beginning, the term looks like a linear equation, the way that happens in the Verhulst or the logistic. The solution grows rapidly. Then in the Verhulst, the quadratic term is negative, and it squashes the problem. In the case of the combustion model, you've got an A of u, b plus u, so that accelerates it. In other words, when you strike the match to it, the solution takes off and the forcing term grows quadratically. And in even one space dimension, you can only go roughly a fraction of a power more than 1 without getting blow up in finite time. In higher dimensions, it's a little bit lower, but if that third term, c minus u, was not there, that model would blow up in finite time. But what happens is u gets large, the c minus u now kicks in, and the combustion, the large growth that you get in the model now gets eventually quashed, and the thing settles down to 0 again. So that's somewhat critical to the modeling, but in our case, it would depend on where we measured. And it depends on the combinations of these A, B, and C. If I can get back to stop screen, yep. We might not measure until that C has not yet kicked in, and you would end up with an F that's effectively running on a quadratic nonlinearity, and you can get very, very large values. Well, for the range condition, that would be rather good. Our range condition would certainly be satisfied, but I don't know whether you would not get considerable problems coming in from the analysis here that you would be unwanted. And of course, if you're looking at avoiding the issues of blow up in finite time, then you have to make a global restriction on F, that it's basically only at most mildly superlinear, and mildly means basically it's only a power 1 plus epsilon. So I don't know how it would change if you made such an assumption. The analysis, would it make up for it? I don't know.
Thank you.
I see questions are There is already one question from the audience, from a colleague from the department. Let me put the question here on screen. Can you hear it? Can you see it?
Yes.
From Wagner.
The noise was put into G of U and G of V. So typically the game we play with noise is we run the forward model. In this case, it's just basically a Crank-Nicholson scheme. And we sample at a certain number of points. 20, 40 points is a typical number we're choosing. And we add noise to those points. And then we extrapolate our data to infinity by putting it through, let's say, a cubic spline or some other kind of interpolation routine. One can build in, at that point, regularization, or one cannot and build it in later with a penalty term. And we've done all of these things. But that's how the noise comes into the G of U. Now, of course, the noise in the G of U and the G of V comes into W. And W appears all over the map, and trying to track what might have been seemingly simple noise in G of U after you've run it through the PDE and got W is not easy to see. And of course, this is just the linear equation set. When you do it through the non-linear PDE, it's even less easy to see what the effects of these things are. This is why the analysis is actually completely non-trivial, and why we'd like to tell you we've got much better results than we actually do. But truthfully, we're actually quite proud of what we've managed to get, given the realities. Does that answer the question?
Well, let's see. He's going to give some feedback.
Okay.
Yeah, we could be. Actually, it's a good opportunity to have the two of you guys here, because I'm very interested in this problem of identifying two different coefficients in the same inverse problem. So some time ago, I think it was 2017, we tried to solve the optimal tomography problem. It's an elliptic PDE, and you have to identify the coefficients A and C simultaneously.
Mm-hmm.
So, and it was quite hard because at some time the coefficients start to interact with each other. And the identification for the C problem is much simpler than for the A problem. And then
Yes.
When you try to do a numerical scheme in order to identify both coefficients, it's very hard to set up the pace for the convergence with respect to the two unknown coefficients. And you have also experience with this kind of problems. How do you deal with that? With the penalization term?
You don't. I mean, in some ways, it's there. I mean, okay, so there's lots of folk theorems in inverse problems. Here's another folk theorem. You have two coefficients. One appears in the leading term of the operator, elliptic operator, in second derivative term, right?
Okay.
And the other one appears in a trailing term. Well, which of these two terms is the most important? Answer, the second derivative term. So that term will dominate. And you saw that, right? You saw exactly that in the recovery of the A and Q. A dominates. And so the folk theorem says if you've got two terms you're trying to recover, the inverse, the one that dominates will make a bigger difference to the data than the one who doesn't dominate. But therefore, the inversion will be easier for the dominant term than for the non-dominant one. And this is true. This is why I gave you this example of Verhulst. Getting the R here was easy. Getting the K, well, it was also easy mathematically, but the sensitivity of K to the data was very different from the R. I mean, the R is the initial takeoff, and you can see that quite clearly, but how it tails off in the end takes a lot longer. And just, okay, I've got I'm teaching a class in epidemics. In fact, just before epidemic modeling to some pretty bright undergraduates. It's really a research class. And just before I came on here, I was talking to them, and they're going a bit crazy here with the fact that in the various coefficients in the epidemic modeling, they're having a hard time extracting one over the other. And it's always going to be the case, right? That's why I mentioned this little piece of snippet about getting the K in the Verhulst equation against the R was much harder. And this is exactly like the AQ problem. A is much easier to get because it affects the solution. And in any coupled PDE, if the two coefficients are not similar, then that problem will be there. The reason the coupled system of the F1 and F2 in the two pairings of a U and V equation work out rather well with a small interaction term beta is that it's two reaction diffusion equations with the same A, are just different F1 and F2. But it's the same strength then. And if they're the same strength, none dominates, and you get a chance of getting them both. The reason it can become more difficult with an interaction term is it can favor one over the other.
Yes.
And now you've changed the game. So this is standard. And every time you've got two coefficients, that's one of the first mental questions you have to ask yourself is, what do I expect here for an answer? And whatever you expect, you will probably get it, but to more further degree than you were hoping for. I mean, just you know this well. I mean, singular values, if they're off by a factor of 100 difference between the two coefficients, you're going to get one and not the other with any noise.
Yeah, this is true.
Yeah, but it's not, what can you do about it? Nothing. It's that other coefficient is hidden in the noise. It's been swamped by the A.
I see. So there is no clever way to separate and to distinguish during penalization, to distinguish the two different coefficients.
You might manage to set some experiments up that give input data that, for example, tries to either term R of U and R of V as a driving term on the right-hand side. That driving term can help do that.
I see.
The question is, how do I choose this in advance? Guess. Not quite, but I mean, it's
an optimization problem. So it could be an optimization problem. So
non-trivial.
Optimum experiment.
Non-trivial.
Mm-hmm. Mm-hmm.
But it's quite easy to see this just even with an ODE problem with two constants, that you can look at the singular values coming out, and the Verhulst equation, just do that one. You'll see that the singular values for the two coefficients are off by quite often a factor of 10 to 20 to 100. And so if you've got too much noise, you can't use the small singular values, and they're the ones that are coming from the other coefficient. And so the answer is simple. You cannot recover that coefficient within the noise level.
I see. Well, you try different tricks like augmented Lagrange and other optimization tricks that you use.
No. I mean, this is the famous quote: "No amount of mathematical trickery can make up for lost information."
Yes.
Right? And so if you've got significant noise in the data, you're trying to invert a matrix, you have to put in some cutoff, and that cutoff is determined by your estimate of the noise. And if that cutoff cuts off most or all of the singular values correspond to your second unknown, that is it. And you might manage to do some shifting of those things by creatively adding in other terms that might might augment it, and that's certainly possible. But then it becomes one of the clever questions is, how do I set an experiment up that will help in this regard? What inputs do I put in that will modify the operator's singular values towards the one that I'm looking for or couldn't find before? It's clearly a good question.
Thank you, Bill. I don't want to monopolize the question section. So there is a question from Louisa. I'm putting it on the screen now.
So the answer to your question is, of course, well, you see, in most cases, when you've got a fixed equation, so for example, the combustion model that was mentioned there, those constants A, B, and C have meanings. And you think you know these things. One is the specific heat of the whatever, and you can determine that. So there's no such thing as really a model in for example, chemical reactions, where you don't think you know those constants A, B, and C to some degree. But there could be, of course, one of the interacting terms could be the unknown part. But one at least, or maybe more than one, is likely to be something like a specific heat or a conductivity of the metal that's there, or one of the metals. And I know that. So we haven't, to be truthful, ran any kind of experiments based on, for example, that reaction term, specifically to analyze that question. So I'm afraid my answer is I don't really know. But again, if it's not quite right, and you put in the estimated values, then in that case, your Newton scheme might actually work much better than it would otherwise. The problem with Newton schemes, of course, is always that you need a good starting guess. And if you've got no clue, then usually the end result is clear. But if you do, and I think it's often a case of physics experiments that you do have that because you know some of the terms, as opposed to, for example, ecological ones where you have no clue what those constants are. But I'm afraid I can't give you a better answer than that, because I'm really not an expert at all, of course, in those models per se for combustion.
Okay, thank you. So far, we have no further questions on the chat. Barbara, do you have any further questions? No. So
I'll get my my score later on, I guess.
I see. Okay, it's already 3:10, so I think it's time to conclude. Thank you, Bill. Thank you very much. Thank you also, Barbara, for coming up and for participating in this conference. It was very nice to see you guys once again. So, well, actually, we do not know when we are going to meet again. But it's this sort of meetings are. It's actually it's a quite nice opportunity to keep in touch.
Yeah.
So, I'd also like to say farewell to the audience, and next Friday.
Thank you very much for your attention.
Yep. Next Friday, we're going to be back with another talk from Professor Katie Tenenblatt from the Brasilia University. So thank you very much for your attention. See you next week.
Okay. Bye-bye.